that you all just turned in. Trust finite element analysis, visual analysis. All right. So I hope that went well for everyone. I haven't had a chance to take a look at them yet, but we'll start grading those this week. And you've got homework 6 due next week, so that's going to be focused on single axis axial force system FEA solved by hand, a beam problem to solve using FEA, and then you'll model that beam in visual analysis, right? So a little bit more practice with FEA and visual analysis all around. And then homework 7, which I haven't released yet, will be focused on dead and live loads and seismic loads, right? All right, so in this handout, the first page is a summary of all the equations that are relevant to seismic design. So I thought it would be nice to just have them all in one place for you, and just for convenience, so you can find it there. I also, I also have this example fully worked out. So the full solution of this example is included at the end of this handout, right, for reference, but we'll work through it in class today. So we'll start off, right? We have this 2-story structure, and we're given that the lateral system is an ordinary steel frame building. So whenever you see something like that where it just calls it a frame building, if it doesn't specify that it's a braced frame, then it's a moment frame, all right? So an ordinary steel frame building, clarify that it is a moment frame if braced is not specified. And I believe it was mentioned in the recorded lecture, right, the distinction between ordinary, intermediate, and special that we see in these lateral force resisting system categories. So I think what I focused on was special more, and said that special frames or special shear walls are detailed so that they are more ductile and they're better able to perform in an earthquake well. An ordinary frame like this would just be, would not be allowed in a lot of high seismic regions actually, because the detailing on it would not perform well in seismic activity. So, so this is supposed to be located in Denver, Colorado. The occupancy is standard, all right? So a standard occupancy, what will that be relevant for? What information does that tell us? Yeah.
Risk factor?
Yeah, that's going to help us figure out the risk factor by first identifying what the importance factor is, right? And then from that, we will determine the risk category, which is also based on, let's see. Oh yeah, well, risk category and then importance factor. Yeah, so I had that backwards, right? So standard occupancy would be risk category 2. And then we're given information about the soil at the site, right? So it's very dense soil and soft rock. We're told that the dead loads that are provided here, 50 kips and 60 kips, include the slab weight, half the column and wall weights between the floors, and partition weights. So you don't have to worry about all those details. In this class, you're not going to be asked to determine what the seismic weight is of a structure. For the most part, it is just dead loads, but sometimes it gets a little bit more involved than that. That'll be saved for an advanced class if you choose to take one. But here, you'll just be given the seismic weights at each floor. All right, and then we are given the location of the site, all right, longitude and latitude. All right, so first step is to determine the design earthquake and the seismic design category. All right, so first, we already noted risk category will come from the standard occupancy. And which risk category do you think that would put us in? Yep, very good. Risk category 2. All right, so most buildings fall under risk category 2 if there's nothing special about it. It won't be 3 or 4, and if it's, standard occupancy, it won't be 1, because that's for places where you don't expect humans to spend much time. All right, and then site class. All right, so from the table, I think we have, I have the copy of some of the relevant tables attached. All right, so we go to this table right here for site classification, find the description over here. Remember I said you don't have to worry about any of these columns for this class. So we were told very dense soil and soft rock, that's site class C. We're going to take that information and use it to figure out our FA and FV values, right? So we'll enter those tables with site class C, and we'll also enter them with the mapped parameters, which we haven't determined yet for this example, but we will go do that. So that's from table 20.3-1, and I'm going through and noting where this information is coming from in the example, because that's what I want you to do in your homework as well. All right, so for the mapped values, we're going to go to that Applied Technology Council website. So that's hazards.atcouncil.org. And we're going to search by coordinate since we're given our latitude and longitude. All right, so the latitude comes up first, so 39.6. And longitude. One thing to keep in mind with this website, west has to be entered as negative. So west and south are entered as negative, north and east positive. So make sure you do that. So I'll enter -105, otherwise you'll end up in China with no values because ASCE doesn't cover China. All right, so that looks about right? Landed us in Denver. I'm gonna switch to the Seismic tab over here and then make sure that we have the correct reference document selected. And remember, for this, we have to input the risk category and the site class. So that's why I identified those first. Those two pieces of information have nothing to do with the mapped values. It's just a necessary input in order to get results from this website, okay? So here, our map values, SS is 0.221 and S1 is 0.059. It gives us all the stuff that we're going to calculate, so we can use that to check our answers, but we're only going to use those first two values for our work. All right, so SS is 0.22 and S1 is 0.059. And then our site coefficients, we can go back to that table. All right, so for SS of 0.22, that falls into this first column. So our FA value is going to be 1.3. For FV, we use S1. And we got an S1 of 0.054, so that also falls into this first column. So we use 1.5. And so remember, if you fall in between the columns, you may need to apply linear interpolation. So just keep that in mind. All right, so FA is 1.3 and FV is 1.5. So these are from tables 11.4-1 and 11.4-2. Now we can calculate the maximum considered earthquake. All right, so SMS is FA times SS. So that's going to be 0.286. And SM1 is FV times S1. So that's going to be 1.5 times 0.059. I'm going to round a little bit here to 0.09. And then we can calculate the design earthquake. So SD1, or I'll keep it in order, SDS is going to be 2/3 of SMS. So that's going to be 0.191. And SD1 is 2/3 of SM1. And that will be 0.06. 0.06. All right, so now that we have determined the design earthquake, right? So it's just these two parameters that define that earthquake, and remember what those represent. You don't have to know too much about this for this class, but those represent, SDS represents the plateau of the response spectra, and SD1 represents the 1 second response, right? So it represents these two locations on that design earthquake spectra. If we were doing a dynamic analysis, we would figure out the entire spectra, all right, which would be something like that. We would figure out that entire spectra, and we would run, depending on the type of analysis, right, we would do a much more involved set of calculations. So, but we're sticking to the static method in this class because it is the most commonly applied and the easiest to learn. All right, so now we can determine that seismic design category. So we're going to use this information, right, the design earthquake, and we're going to use this information, risk category, in these last two tables over here. All right, so for SDS between 0.167 and 0.33, and risk category 2, we get a seismic design category of B. And then remember, you have to check both tables and use the worst case. So here, SD1, we found to be 0.06, so that falls into that first line. For risk category 2, that tells us seismic design category A. So which one do we use? Right, we use B. So from table 11.6-1, we got SDC of B, and from 11.6-2, we got SDC of A. So we want to use that one. And in your work, right, I would like to see you show that you checked both, right? Report what they say and then show which one you're selecting, right? Sometimes they show up the same, but not always. Any questions so far? All right, so if we, at this point, let's just kind of quickly go back and check that website, right? So we got a design earthquake, SMS 0.191, SM1, or SDS, right, and SD1 here, 0.19 and 0.06. So what did we see for SDS? 0.192 and SD1, 0.059. So we got it right, a little bit of rounding error involved, but pretty close. All right. Oh, also what this website will tell you is the seismic design category, right? So that's the first line under additional information. So we got that correct. You can also verify your site coefficients down there, right? FA and FV. And then all the other stuff is beyond the scope of this class. You don't have to worry about it. All right, so the next phase is to determine the seismic forces, right? Now that we've identified the design earthquake and the design category. So find the seismic forces. At this point, we will need to know the importance factor. So our IE for risk category 2 will be 1.0, and that's just from the table 1.5-2 on the first page of the environmental loads handout, right below the risk category table, right? And then we'll note what our approximate natural period is, right? So we're going to use the TA equation that the ELF allows us to use. So that's going to be equal to a coefficient CT times HN raised to the exponent X. All right, and so from table 12.8-2, which I think I do have that one also. So that's the third page of tables in the handout, in the example that you're working through now, right? So this table right here is where you go to find CT and X, all right? So it's based on the type of structure you have. And since we have a moment resisting frame where that is the only lateral force resisting system in the building, we can use, or at least in the direction under consideration, which in this case is both directions, have the same structure, so, or same system. So we use this value here for steel moment resisting frames. So CT will be 0.028 and X will be 0.8. And I think I went over this in the lecture as well, but if we had a braced frame and a moment frame, you know, side by side in a given direction of the building, then we wouldn't be able to use this category because the moment resisting frame, we can't say for sure that it's designed to resist 100% of the required seismic forces, right? Now, if you were the structural engineer of record and you decided to make sure that the moment frame by itself could do that, even though you still have a braced frame, that's up to you, and then you could use this value, right? But unless that were the case, you would want to use the all other structural systems. But in this example, since we only have the moment frame, we're going to use the steel moment frame values. All right, so back to our notes here. CT is 0.028 and X is equal to 0.8. So that's from table 12.8-2. And so we can calculate our approximate natural period. It's 0.028. And what is H? Anyone remember what's HN? Yeah, it's the height to the highest diaphragm level above the base. So in this example, we were given story heights of 12 feet each. So 24 raised to 0.8 exponent. So that gives us 0.36 seconds. All right, so that gives us IE and T. We also need R, right? Because our goal here is to determine that CS factor, which is SDS divided by R over IE. And the T comes into play in one of the limit checks, right? So the last thing we need before we can calculate CS is R. All right, and R depends on what? It depends on the type of lateral system that we have. Yep, what else? Yeah, that's it, actually. So R depends on the type of frame. So we have an ordinary steel moment frame. So we're going to go to that long table right here, and let's see, I'll rotate it. All right, so in the moment frame category, we just scan the list until we find our steel ordinary moment frame. And then our R value is 3.5. So R is equal to 3.5, and that's from table 12.2-1. And a quick check, all right? We have seismic design category B, which is this first column over here. So looking across, there is no limit on this particular structural system in seismic design category B, okay? If we had seismic design category D or worse, we would not be allowed to use that structural system, okay? So in the high seismic categories, we would have to use intermediate or more likely special moment frames, okay, not ordinary. All right, but it is permitted in seismic design category B, so we're all good. So now we can calculate our CS value. So CS is equal to SDS divided by R over IE. SDS was 0.191, and we had 3.5 and 1. So we get a value of 0.055 for our CS. So this would represent 5.5% of the weight of the building is going to be our base shear. But first we need to check the limits, right? We have some lower and upper limits to verify. So CS has to be greater than or equal to 0.044 times SDS, which is 0.191. And IE, which is 1. So that's going to be 0.008. So we meet that criteria. We also have to meet, right, a minimum of 1% of the weight of the building, and that is also met. And then we have an upper limit to check. So CS doesn't have to be taken larger than SD1 divided by T and R over IE. So we'll calc that. SD1 was 0.06, and our T was 0.36. So this gives us a value of 0.048. Since the upper limit is less than the value we calculated up here, that's great. That helps us out. We're going to go ahead and use a smaller CS value that lessens the percentage of the weight of the building that we have to apply laterally. It lessens our lateral load. So we're going to use this. And as I mentioned in the recorded lecture, this upper limit is technically optional, right? The wording in the standard is that CS need not be taken greater than this value. So if you wanted to, right, you could be conservative and stick with the value you calculated, but this helps us out. All right, so now we can calculate our base shear. So V is equal to CS times W. So 0.048 times total seismic weight was, we were given 50 and 60 kips respectively for the two floors. All right, so that gives us 5.28 kips. And now we distribute it vertically. So that's the third part of the problem. All right, so our equation that we need, the new calc that we need is for this CVX factor. This is going to determine what portion of the base shear gets applied to each level. All right, so it's got to be calculated once per each level above the ground, and that formula is the weight of that level under consideration times the height of that level above the base, from the base, raised to an exponent k, divided by the summation of that product for each level above the base. and then the lateral force is equal to CVX times V for each level. So in this problem, K is equal to 1, right? So remember that K is related to the natural period of the structure. If we go back to the first page in this handout, that is described down here. So if you have a period of 0.5 seconds or less, K is equal to 1. That's also included in the lecture slides from the recorded lecture. So we'll note that here. So K is equal to 1 since T is less than 0.5 seconds. I think it's less than or equal to there. All right, so there are a couple different ways to go about this next step. I like to organize things in a table. It's not really that crucial for a shorter structure like this that just has 2 levels, but when you have a taller building and you have a lot of levels to do these repetitive calculations for, it's really nice to organize it in a table, and then you can just systematically, put it in Excel, really is what I do. But you can go through and calculate each item systematically. So I'm gonna construct a table to show you that process there. So we'll call the level X, right? And that's the level above the base. So we have 2 and 1. And then the height to that level from the base in feet. All right, so it's 24 to level 2 and 12 feet to level 1. The weight of that level above the ground in kips, that's the seismic weight associated with each level. We had 50 for 2 and 60 for 1. So then the numerator would be this product, WX times HX raised to the K exponent. So this would be 50 times 24, or 1200. And then 60 times 12, or 720. We also need the summation of that product for the denominator, right? So summation is 1920. So then we can calculate the CVX value using this equation right here. So that's just going to be 1200 divided by 1920 for level 2, which is 0.625, and then 720 over 1920 for level 1, which is 0.375. And as a gut check, right, the summation of the values in this column should be 1, right? Meaning that, yes, we are distributing the entire base shear to the building. And then our force, the equivalent lateral force in kips, we just take our CVX, 0.625, times WX, right? The weight associated with that level. Or sorry, no, that is incorrect. What did I mess up? What should it be? CVX times the base shear. So the 5.28, right? So that is 3.3 for level 2, and then it will be 1.98 for level 1. So again, a gut check. The summation of those forces should be equal to the base shear. And then if we want to sketch this, all right, we'll have our forces applied at each level. So 1.98 kips at level 1, and then 3.3 kips applied at level 2. And the base shear should be equal to the summation of those equivalent lateral forces. Okay. Any questions? Questions about seismic loads in general? Yeah.
I noticed in the lecture there was sometimes limited height based on
Yes.
the seismic area. But you also said that taller buildings tend to do better because of the way they move.
Yes. So why? Yeah, that's a great observation. Good question. So certain structural systems will not perform well in seismic regions, right? So so that's why you have like the range of either not permitted, no limit, or a height limit. And actually, I've been told this by someone who was on these committees who knows the reason that there are height limits of like 160 feet or 250 is mostly arbitrary. It's a compromise between people who don't agree. So that's how they choose those height limits, based on, you know, how well a structural system is expected to perform in a certain high seismic region. Yeah. But yes, in general, taller buildings, they tend to be more flexible and more ductile. They tend to fall in the longer period section of the response spectra. All right, so we go, just sketch it here. All right, the response spectra like that. Taller buildings tend to fall over here with the longer period. And so the reason that they tend to perform better is because the magnitude of the earthquake that we need to design them for is a lot smaller, right? So a shorter building in the same region would fall here, right, where the magnitude of the earthquake that we designed for is a lot larger, right? So there's a couple different things going on with that comparison. But yeah, that's a good observation. Yeah. Did you have a question, Alex?
Yeah, I wanted to see if we could talk about the limits, why you chose the 0.048.
Sure. So for CS, because we calculated at the upper limit to be less than the value from this equation, right? So this equation gives you, right, the standard CS value, but it's subject to these limits. So if this value is less than your lower limits, you have to use whichever of these two values is larger, right? So actually, whichever of these three values is largest, right? So I can add a note here that says use the largest, all right? And then from whatever value comes from that, and this one, you would use the smallest. All right, because, well, this is a requirement, right? Using the largest value of these three is a requirement because you can't go lower than these values. Using the smaller of these two is optional, right? So since we got a value here that's an upper limit that's smaller than what we calculated here, we want to use this value because it'll give us a smaller base shear, smaller forces to distribute above the base, right? And that helps us out with our design. Yeah. Any other questions? All right. Well, we're out of time. So Friday, we will start talking about wind loads, but I'll also have a few fun things to show you related to seismic loads and wind loads. To start off with, all right?